Good morning all of you. So here in this video I'm going to discuss I'm going to introduce a magnetostatics concept of this magnetostatics. So till we studied the electrostatics, that means we studied the properties of charges when charges are at rest. Okay, so when charges are at rest we study so many properties, field lines, how field lines will produce it, divergent of these field lines, electric field lines, curl of these electric field lines, potential of these field lines. Okay, so dipole moment, potential due to these bound charges, these are all we studied in electrostatics, right? So here in magnetostatics, here the charges are moving with respect to time, but here we discuss it by taking a steady current. In magnetostatics we study the properties of magnetic field produced by this steady current. Let's see, let us take a small wire. So this is our small metal wire which carries a current I, in this direction. So if I bring a test charge Q nearer to this metal wire carrying a current I at point P, if I place the test charge Q here, it does not experience any force. In electrostatics we studied that if suppose there is a charges Q1, Q2, Q3, Q4 like that, if these are our source charges, if I bring a test charge Q nearer to these source charges, it definitely experiences some force. Due to why? Because these test charges produce an electric field. This electric field causes a force on this test charge Q. In electrostatics we studied this one, but these source charges are at rest. But here in this case the charges are moving with respect to time. The current is produced, there is a current in this wire, but this test charge does not experience any force. Why? Because these metal wire are electrically neutral. Equal number of positive charge and equal number of negative charges are distributed. So these are electrically neutral. Electric field does not affect this test charge Q. But when these test charge start moving, it means it's projected in the direction of this moving current, then it experiences some force. So this force is different from that electrostatic force. Okay, so this moving current produce a magnetic field B. The magnetic field can be represented with the symbol B. This magnetic field cause the force Q. This magnetic field exerts the force on this test charge Q, and the force produced by this magnetic field, so magnetic field, this magnetic field is produced by this moving current. This moving current produces magnetic field. The charge can feel this magnetic field only when this charge start moving. Okay, so and the magnetic force due to this magnetic field, okay, the force exerted on this charge Q due to this magnetic field is called magnetic force. Okay, so let us see some more properties of this magnetic field and magnetic force with for this test charge. The charge moving in the same direction, different direction. So what will be the force and what will be the magnetic field, and what are the directions of this force and magnetic field? Okay, let's see. If suppose the speed of the charge particle, test particle Q is V, if the speed of the particle is V and it makes an angle theta with the magnetic field, then the magnitude of the force is proportional to V sin theta. That means the force produced on this charge, the magnetic force which produced by this magnetic field on this charge Q is proportional to V sin theta. It depends on velocity of the charge particle and also how much this test charge Q makes an angle theta with magnetic field B. Okay, this is theta, if suppose this is B. So if I write like this, it indicates that the magnetic field is into the bold, means field lines are like this. If I write dot and circle around this dot, then the magnetic field is out from the board. Okay, here the magnetic field is inside to the board. If the magnitude of this force, that means the magnetic force on this charge is directly proportional to the angle theta, which makes between the velocity of the particle and also magnetic field. Okay, next, the direction of the magnetic force, is perpendicular to the direction of magnetic field as well as the direction of velocity. Okay, so that means if suppose this is my magnetic field direction and this is velocity of the particle, then force is always almost perpendicular. So perpendicular to those magnetic field and as well as velocity. So the direction of the magnetic force is always perpendicular to the direction of magnetic field produced by this current wire and also velocity of the charge, this test charge. Okay, and the force is proportional to the magnitude of the charge q and its direction is opposite to the positive and negative charge. See, that means is also directly proportional to the magnitude of the charge q, okay, into v sine theta. C, we can write this as f is equal to q v sine theta. It is depends on magnitude of the charge. That means if it is plus phi q, here we can write this as plus phi q. And also direction opposite to the positive and negative charges means, so f is equal to q v sine theta. If suppose here if we take this q as a positive charge, if we take q as a negative charge, f is equal to minus q v sine theta, and the direction for this q and this q, the force is opposite. Here only we can take this force is opposite directions. If here the q plus q indicates if it is x-axis, the negative q indicates the force is in negative x-axis direction. Okay, the magnetic force on this charge q is proportional to the magnitude of this charge. That means it is plus phi q, to take is a plus phi q. If it means it increases the force. If it is a plus phi q, the force is more. If it is plus 6q, the force on this charge is more than this plus phi q charge. So it depends on the magnitude of the charge. And also the force direction is opposite to the charge. It depends on positive either negative charges. Okay, and so by measuring the force acting on this charge q, that means by measuring the magnetic force acting on this charge q, we can easily calculate magnetic field also. If suppose the magnetic field B and velocity of the particles are parallel to each other, then the force is 0. Why? Because the magnetic force F is equal to Q into V cross B. Why? Because V is velocity of the particle always perpendicular to the B magnetic field almost. Okay, next, so F is equal to, if suppose V is, then we can write this as V B sine theta. If V is parallel to B means angle between them is 0. If you substitute 0 here, Q V B into sine 0 is nothing but 0, therefore F is equal to 0. If suppose velocity of a particle and magnetic field produced by this current are parallel to each other, then angle between them is 0, so then F is equal to 0. That means magnetic force acting on this charge is 0. The force is maximum only when exactly this velocity of a particle is perpendicular to the magnetic field. If suppose angle between them is 90 degree, then force is F is equal to Q into VB, because sine 90 is 1. So this force is maximum. The magnetic force is maximum on this test charge Q only when velocity of a moving particle, this particle and the magnetic field makes an angle theta is equal to 90 degree. Okay, next, so this magnetic field, what is the SI unit for this magnetic field? So this magnetic field SI unit of magnetic field is the SI unit of magnetic field is Newton per ampere meter. Also we can represent this magnetic field in SI unit as Weber per meter square. We can also write SI unit for magnetic field as Tesla, which can be represented with the symbol T, capital T. So while writing the unit, we have to write this in small. The letter will start with small letter. Okay. Next, we can also represent this as Gauss. SI unit for magnetic field also Gauss, which can represent by G. But Tesla is very big amount. So 1 Tesla is equal to 10 to the power of 4 Gauss. 1 Tesla or 1 T is equal to 10 to the power of 4 G. Okay. So next, in the next video we will discuss the what are these. If we place a magnetic field, this moving current on the external magnetic field, so what type of force exert on this magnetic field on this current. Okay. In the next class we will discuss some more properties of this static current and magnetic field.